Okay, let's have a little more fun. So let's say I've got my beta D-glucose here, beta D-glucose. And let's say I react this guy with any alcohol. And technically, you need a little bit of a catalyst, acid or base. So I'm putting an acid catalyst. Actually, you just need acid catalyst, my bad. A little acid catalyst in my alcohol. So, and in this case, alcohols don't react with other alcohols. They don't. But they react with hemiacetals and hemiketals. And in this case, that OH gets protonated by the acid and leaves as what? Water. And what replaces it? The alcohol. And so in this case, cool. How do you find your anomeric carbon now? Yeah, bonded to oxygen still. So he's always next to oxygen in the ring. He's just the one that's bonded to two oxygens. And in this case, he's still bonded to two oxygens, but is either one an OH now? No, they're both oxygen-carbon chains, oxygen-carbon chains. That is not a hemi anymore. It's a full-blown, in this case, acetal because it came from an aldehyde. Had it come from a ketone, it would have been called a ketal. And in this case, acetals, this thing's locked. You can't mutorotate an acetal. He's not going to be, going back and forth between the alpha and beta acetals. Doesn't work that way. So it also turns out that when you're an acetal or a ketal, you're what we call a non-reducing sugar. What do you suppose we mean by a reducing sugar? It's a sugar that can act as a reducing agent. Okay. What happens to the reducing agent? Anybody remember from Gen Chem what happens to the reducing agent? Gets oxidized. Here's the deal. Aldehydes can get oxidized. What can aldehydes get oxidized to? Chromic acid would do it if you remember your OChem. Carboxylic acids. They become carboxylic acids. Sweet. Now ketones, it turns out, ketones are not the easiest things to oxidize. But we got two routes. One, turns out you can isomerize this through the enol, and it'll probably be a little bit of the corresponding aldehyde sugar present. So just an isomerization process present already in the solution. And because it is a small equilibrium of this present, as soon as I would add something that needs to get reduced, this guy would be like, sweet, I'll get oxidized. And the little equilibrium that this was present in, as soon as this disappears, more of it would have to form according to Le Chatelier's principle. And eventually all of this turns into this, and all of it gets oxidized into a carboxylic acid. So even most ketoses turn out they're reducing sugars. In the open chain form, any sugar you see is going to be a reducing sugar. The only time you got to worry about it being non-reducing is if it's in the closed chain form. Now in the closed chain form, if it's a hemi, it's still reducing. You can reduce these. One, because they're in equilibrium with the open chain form and that whole process of mutarotation. Two, it turns out you can actually just reduce it in the cyclic form. You can oxidize it, in the cyclic form just as well. But either way, hemis, hemiacetal, hemiketal, they're also reducing sugars. It's only when you have a full-blown acetal or a full-blown ketal, they are not reducing sugars.